Hello, this is Rick Powers coming to you from my home office for Western Technical College. Introductory statistics using SALT for the binomial distribution. I'm hoping that you've looked at the binomial distribution in terms of the videos that I have out there explaining it. But we're going to go through right now. I'll show you how to use SALT in order to find information about the binomial distribution. So I'm going to share my screen here. So I'm going to go out to a particular question on homework. And this is from homework set number 7, problem number 8. And we're looking at testing student cholesterol levels. And we are going to test 14 students. And we know ahead of time that the probability of having a healthy cholesterol level is 0.20. Now, as you hopefully recall, what we're looking at here in the binomial distribution is that we have, first of all, a given general probability. In this case, it's the 0.20. So that number, 0.20, is P. That is the overall probability of a success. For each individual student, we consider that there's a 20% chance that they have a healthy cholesterol level. Oh, that's not very great, only 20% have healthy cholesterol levels, but we're pretending here. We don't know what that number actually is in real life, but we're just saying, let's suppose that that's the case. So then when we are doing a binomial situation, we have the binomial means there's two options. Either they have a healthy one or they don't. That's it. So we've got those two options. And then we say we're looking at a fixed number of trials. So there is a certain number of times that we are observing here. And that would be the 14. We're observing 14 students. And so again, the probability of success is 0.20. That's the answer to part B. So what is the real question here? The real question is, what do we expect to happen in this group of 14 students? How many of them do we expect to have healthy cholesterol levels? Well, it turns out there's a pretty complicated formula out there that's based on mathematical ideas that allows us to say if people are randomly chosen and if the probability of the 20% is true for each one of them, then we have an idea of how many, or I should say, of what to expect regarding the number of students, but it's based on the concept that we don't know for sure. We have a probability of success. And what we're looking for then, our variable, which we call X, is the number of students out of the 14. And just like when we did discrete probability, we have an X and we also have a probability of X. We have the number of students out of the 14, and each one of those numbers might happen. And so then the question is, how likely are these things to happen? So we're asking the question, how many students do we expect to have a healthy cholesterol level? And in addition, we would say, what is the probability of those different number of students? Now, if it's a 20% chance, then to have all 14 of them be healthy, well, that's probably not going to happen, right? So what we're going to do is we're going to use SALT in order to understand how this works. So I open window and I type SALT, and I know where that is, and here it comes. So salt is coming up. Now we don't have any data to put in here. There's nothing going on like that. We're looking at the distribution calculator. So we pick distribution calculator, and then we go over here and we choose the binomial distribution. And then we fill in the correct numbers. The number of fixed trials we said was 14. And the probability of success we said was 0.20. Now, right at this point, we have a graph of all of these things. And it's unfortunate that salt doesn't have very good size of the type here. These numbers are really small, but I can read them, and hopefully you can as well. Well, what is this telling me? It's telling me that there's different levels of probability. And let's just choose here the probability that x is less than or equal to 0. Well, that would be here, 0. And notice I can choose up here on the right-hand side whether I'm looking at the left side of the distribution, or I could have, if I wanted the right side, notice when I change this to be right tail, then it says greater than, that changes the symbol. So the symbol here about what x values I care about is related to what I have here. Now, certainly, it might be that we want the left side or the right side, or we could want both tails. And how it's listed here would be less than or equal to 0, greater than or equal to 3. And you can play around with this and you can make this happen. And then we also have a between possibility where it's greater than 0 and also less than 3. So that, or less than or equal to 3, greater than or equal to 0. Notice it has an equal sign on these to keep track of that so that we know what's going on. And then if we just want one of these, we say, I don't want this whole thing about different numbers. I just want to know what's the probability that nobody is healthy. That would be the probability that x is equal to 0. So I have 14 students. I test them all, and I say, is it possible that no one is healthy? And the answer is yes, it is possible that nobody has good cholesterol. Well, what is the chance of that happening? Turns out it's about 4%. So then if I say that that's my probability, it would be unusual. If I have 14 students, it would be unusual to only have 0 healthy ones, right? There's a 20% chance of being healthy that I would have 14 and absolutely none of them would be healthy. Well, it could happen. It still could happen. I don't know for sure, but it's not very likely. So now if I'm doing the equal, up here on the right-hand side, again, notice it says equal. And I say, well, what about having just one person that's healthy? That's about 15%. And I could go through and do all of them that way. So if we're looking at this and we say, how do I understand what's going on here? There's a random chance, a 20% chance that I've got healthy cholesterol. And there's 14 people in the class. And when I look at them, I don't know how many of them might have healthy cholesterol until I actually test them. But if they're randomly chosen, then this is what I expect to happen. Again, there's a formula telling me this. It's just like flipping coins. If you flip a bunch of coins, you don't expect them all to come out heads or all to come out tails. It's somewhere in between. Same thing is true here. I don't expect there to be 0 people healthy necessarily. And I certainly wouldn't expect all of them to be healthy because it's only a 20% chance. These bars represent what I can expect to happen. But notice that if I look at, for example, 2, if x is equal to 2, which is a high bar here, that number is just 25%. So is it going to happen? If I have 14 students who walk in and I test them for their cholesterol, it could happen. It's more likely than other things, but I still don't know. I can't, it's only 25%. So I don't really know for sure what's going to happen. It could be 0, could be higher, could be lower, could be 2, 3, maybe 4. Any of these are possibilities. So then this is a mathematical way to describe all of these possibilities. Now, if I want to answer the homework question, and most people are interested in answering their homework questions, the homework question says, what is the probability that exactly 4 out of the 14 students have healthy cholesterol? And I'm supposed to round it off to 3 decimal places. So then if I say, well, exactly 4, that's just the number 4. So that's 0.172 when I round off, and that's the answer. So SALT is giving me a way to find the answer to my homework, which is good, right? But I would like for you to see what's happening here. That we have, if I'm going to ask the question, what do I expect when I walk in the room and I test all these students? I can't say for sure, but I can, in a sense, eliminate things that I would consider to be unusual. So is 0 going to happen? Most likely not. So I take 0 out of the running. Well, what about these other things out here? If I just look at this and I say which ones are less than 5%, looks like 6. So if I say 6, that's 3%, and clearly it goes down from there. So then I would not expect 6 or 7 or 8 or 9 or all the way up to 14. So then what do I expect to happen? I walk in the room and I say, I think there's going to be between 1 and 5 students who are healthy in their cholesterol. I would be surprised if nobody was, but I'd certainly be surprised if I had 6 out of the 14 that were healthy. So now I have an idea of what might happen. I don't know whether it's 1, 2, 3, 4, 5 or anything, but I do know what to expect when I walk in the door. If that 20% is realistic, and if these are just random students, there's not something weird going on with their cholesterol because of the drinking water or something, who knows. And this is what statistics allows me to do then. This is the same thing that happens when you go to the doctor and the doctor says, well, I think you should put this ointment on your cut so then it won't get infected. Do they know exactly what's going to happen? No, they don't, but they have an idea that most people, when they put this ointment on there, that it's not infected anymore and they get better. Or treatments for any other kind of health condition. Or you go into, and this is what happens for your job, hopefully. When we talk about a data-driven decision, they're going to be able to say, if you do this thing in this setting for the people that you're working for or with or whatever, then you can expect these kinds of results. We don't know exactly what's going to happen, but it's going to make this kind of an effect somewhere in this interval, which would make things better. That's what we're all about, right? Making stuff better. So if we know that something might have a good effect, then we can say, well, we're going to do this thing because the data show that it has a particular effect. I mean, everything about COVID-19, right? All these different treatments that are out there. Do they work or don't they work? Well, they might have some effect, but is it a significant one? How do we know? Well, we just give it to people and we find out. And then we don't give it to other people and we see if there's a difference. But we don't actually know what's going to happen. And even after something happens, we're just saying, well, we think it's within a certain range of things. Again, each individual is going to have different reactions. We don't exactly know. But statistics is going to guide us into a data-driven decision, which will give us some idea of what to expect based on a mathematical understanding of what's going on with the thing, whatever it is. Now, there's all kinds of issues which we don't have time to deal with, but at least right now, what we can do is we can say, if I know the percent chance of this happening, and I have a collection of people, the binomial distribution will tell me the probabilities of having success for all these 14 people, and then I can figure out what's the most likely thing to happen and what are things that I would consider unusual, which would be either higher or lower. I should say the ones that would be low in probability, below 5%. And then if I dismiss those, then I'm going to have an interval of expected things, things that I expect to happen. All right, so there's your tutorial about how to use SALT in order to find binomial probabilities. So best wishes on using this for this subject.